So let's talk about nuclear fusion. Welcome to the Thought Bistro podcast with Akhil and Vishrut as we deep dive into a variety of interesting and thought-provoking topics. Join us as we explore the world of ideas and broaden our collective horizon.
So what is nuclear fusion? Nuclear fusion at the base of it is a very straightforward concept. It's the concept of two small things bursting into each other head first and forming a bigger thing. And during the formation of the bigger thing, there is some of the energy released. Now, as straightforward as it sounds, humanity, despite having known how to do it for some 50 odd years now, has not been able to achieve more energy out than it is needed for the reaction to occur. Kind of think of it in this manner. You know how there's this girl in your class who you really dislike and you just can't stand her. And slowly and steadily, there is this spark that happens and you guys get together. And the hate that used to be there, now the love that is there completely overpowers it and overshadows it.
So basically what you're saying is that the effort and energy it takes for me to get to that spark has to be worth it. You're saying fusion has not been able to be worth it yet. The spark has fizzled out.
Exactly. So that love is just not enough. Every time they go out on a date, they're like, oh no, maybe I don't like her. While it should be like, oh my God, this is the one. And, she's the one. That's how it
He is
should
the
be.
one for me.
She's the one for me should be the answer to fusion, right?
The other way I was thinking about it was that, how in maths you have to get 2 plus 2 equals to 4, right? Here you don't have 2 plus 2. Here you have 2 plus 3, but you still want to make 4. So you're getting a 4 plus a 1. That 1 is the thing that is making the energy because the 4 is the bigger thing that you're talking about.
Exactly. So getting to that, basically, as you've heard, as I just told you what fusion is. So to get to that extra one, what we need is hydrogen. And plain old hydrogen does not work. So plain old hydrogen has one proton to it. A heavy hydrogen has one proton and one neutron to it. And by the way, for our listeners who are not aware, a proton, a neutron, and an electron, these are the basic building blocks of an atom, as we've learned in primary school, and hopefully you have as well. A heavy hydrogen has one proton and one neutron to it, and we call it a deuterium, deut standing for two. And a hydrogen with one proton and two neutrons stands for a tritium, tri standing for a three. So that becomes a fairly straightforward thing to learn. For fusion to happen, we take one deuterium, which is a hydrogen with two, and one tritium, which is a hydrogen with three. And we just bash them together as hard as we can, and it makes helium-4, which literally means helium with two protons and two neutrons. And if math sits right in your brain, that should leave one neutron standing. And that leftover neutron is what we are looking for. That leftover neutron is the holy grail of energy that we are after.
Yeah, so I'm just saying it's just going back to that example. 2 plus 3 is equal to 4 plus 1. That is what you have to achieve. So now, as you know, that there are two types of nuclear reactions that can take place. So one is called fission and the other is fusion. Now, from whatever I remember in school when I studied this first in physics in the 7th or 8th grade, it was always told to me that there are two types of nuclear reactions, fusion and fission. Fission is something that we do on a regular basis, and fusion is not achievable, but it takes place on the sun. Now, the reason that they say fusion is not achievable, or they said fusion is not achievable to us students, was because fusion on Earth requires very, very high temperatures and very high pressures because you have to essentially recreate the conditions that occur upon the sun.
So the two ways that we are able to achieve these kinds of temperatures and that kind of pressure are, again, to think about it conceptually, they are pretty straightforward. One is you take a bunch of these deuteriums and tritiums and you just shoot them towards each other. And you hope one of them hits the other with like just the right amount or more than just the right amount. And we'll get more energy out. However, to do that, what tends to happen is it takes so much energy to accelerate them towards each other that what we get out is just not worth the effort.
It's a fraction of what the energy that's required to accelerate these particles to the speeds that they need to achieve, that so that when they bump into each other or when they collide, this reaction takes place.
Exactly. Think about you and me. We are standing like at a distance apart. Both of us have these guns in our hands or Nerf guns in our hands. And we are trying to make the Nerf guns bash into each other, right? Now, make the Nerf guns like a billionth of the size smaller than what they are, maybe more than a billionth of the size smaller, and then try to hit them towards each other and get them exactly right in the exact right location.
There's too many variables.
Yeah, and that is too many bloody nerves. It takes too much effort, right? So it's not worth it.
Yep, too much wastage.
The other way to do this is to generate something that is called plasma. Now, not to scare you away with the term, plasma, just as it sounds, is a very hot mess of these two substances. It is a very hot mess of deuterium and tritium. Now, when you throw something in that hot mess, that is the hate between that girl and the guy. And we just have to heat it up high enough and then let it be there for long enough. You know, you might be in class for some time and not like each other. And it's not just that you don't like each other, it's that you dislike each other. And you continuously hate each other. And suddenly that hate switches to love, right? And that's what we get by heating them so high.
And there's a reason why these particles hate each other. Again, I'm going to get to the little physics of it. There are protons and neutrons. Neutrons have zero charge. They are not positive, they're not negative. Protons have a positive charge. Now, if you all remember, again, studying this in school, that two objects that have the same charge repel each other. They are the same, but they repel each other. So you have to get past this repulsive force. You have to, as Akhil is saying, you have to generate that heat. You have to generate that chemistry, that steaminess between the two particles so that they can overcome their repulsive force and get to a distance wherein this extremely strong fundamental force of nature, known as the strong nuclear force, can take effect and these two particles can merge.
So, the challenges that we face during fusion is that this plasma cannot be held inside walled chambers. Because if kept inside walled chambers, that heat just fizzles out. And as soon as that heat will fizzle out, there is no chance of fusion actually taking place. So, what happens is we need to create a magnetic chamber. Basically, imagine like a lot of magnets around a lot of liquid metal, and the liquid metal is just floating in the middle of that like a ball.
Think of levitation as a concept. Like, if you are familiar with levitation, it's when something is suspended on top of another object without actually coming into contact with that object. So here, what they are doing is they are creating a ring of these magnets between which this plasma is suspended. So it is essentially like levitation, but instead of hovering, this is a way of keeping this plasma contained within a certain space without that plasma coming into contact with that space, so that it then loses the heat, which is what creates fusion.
And now this heat that has been supplied to this plasma is retained by the plasma within those walls because there is no escape for that heat. And eventually, one of these deuteriums will hit one of these tritiums inside this very little plasma, and we will get our fusion and we will get our energy out. Now, in this case scenario, we can theoretically get positive energy out. We can theoretically have something that we call a positive Q value. And Q value, again, not to scare you off, just means energy out divided by energy in. And if we can get excess energy out without the waste that nuclear plants produce, that is the holy grail which we humans have been seeking. And despite knowing about it for 50 years, we have not been able to achieve it up until last week.
Yeah, so I mean, think about not even just nuclear energy. I mean, any energy today with fossil fuels and I mean, most of the forms of energy that are prevalent, the basic issue is the waste product that's generated from that energy. Here we have a form of energy which is sustainable, which occurs in the sun on a second to second basis, and something which we have known about, as Akhil said, for the past 50 years.
A question we should also answer is, where do we find this deuterium and tritium, because they sound so fancy? And are they as difficult to find as uranium 235, which is the raw material used in fission?
Deuterium is actually very, very prevalent. It's found in seawater abundantly. So there is no shortage of deuterium on the earth. However, tritium is the element which we run short of. So currently in the world, we only have 20 kilograms of tritium. So there's a lot of countries that have been doing a lot of research into how we can make this viable. So when you talk about making it viable, the USSR as it was, or Russia as it is now, developed this machine known as the tokamak reactor. Now, what this tokamak reactor does is, as Akhil said, it has this chamber of magnets within which a plasma is heated in order to create the fusion reaction. Now, if we look at the first challenge that we mentioned with nuclear fusion, which is the availability of tritium, what the tokamak reactor does is it has a layer within it which allows for tritium to be produced as fusion occurs. So your supply of tritium is being constantly replenished. So that was the first challenge. The second challenge is getting net positive energy out. So if we have to use nuclear fusion as an energy source, we want it to give us more energy out than we have to put in to heat the plasma, right? So that's what's happened in the past week. The Lawrence Livermore lab in Livermore, California, has successfully conducted a fusion experiment using lasers, which is a completely different thing. So that concept is known as inertial confinement fusion, which uses lasers to heat up the plasma. And what they have achieved is that by putting in 2 megajoules of energy, they have gotten out 3.5 megajoules of energy, which is 1.5 times more energy that's come out as compared to that put in. So this has been a breakthrough for fusion, as earlier we've not achieved a Q value of in the positive. We've not even managed to break even. So this is huge for the world of fusion.
I think for all the investors listening to our podcast, that is about 50% return in less than 1 billionth of a second. Can you believe it's better than the Tesla stock? And that's all we're after here.
Yeah, I mean, think about it. You put in 100 rupees and you get back 1.5x that in what, 20 billionths of a second, as I think it is.
It was some crazy number. The guy came out in their official video. We are going to link all of these videos that we went through, and we are going to link them in the information of our podcast for all our viewers to go through them as well.
Yeah, if any of you want to deep dive on fusion, there is so much out there. The both of us have spent the past few days just diving into this world of fusion, and our heads have been blown wide open because we did not know that this entire history that existed for nuclear fusion, because it always, to me, as I said earlier, it seemed like it was a pipe dream.
And the aim here is not to scare people off from, oh, this is a very difficult topic. The aim here is to send you deeper down this rabbit hole and deeper down into this source of energy that has been untapped, and that's, looking for more and more development into it. And finally, this recent breakthrough. Vishrut, can you explain the breakthrough more? How did they achieve what they achieved?
So the way they've done it is that they've created these small pellets, which are about 2.2 millimeters in diameter, which is housed in a small cylindrical chamber. As we mentioned earlier, that this pellet cannot touch the walls of the chamber or it will lose its heat. So what they have done is that they have taken 192 different lasers and pointed it all at the cylindrical chamber and heated the chamber, which has in turn heated the pellet in order to create a fusion reaction.
Basically, the teachers have given the dude and the girl a detention in a very, very small room that, there can be enough heat for something to happen. And something did happen, and that's what we are all celebrating here. Last week, it was a big, big breakthrough for humanity as a whole. All of this investment that has gone in over the past couple of decades is now coming to fruition. And that's what it's all about.
Yeah, and the other biggest thing about fusion, which I mean, I'm going to mention because this was the first thing that I remember thinking about when I had no idea how this worked, is when you hear nuclear, you think, oh my God, what if it goes wrong? Is it going to be another Chernobyl? Is it going to be another Fukushima? That's not the case because we're dealing with pellets which are 2.2 millimeters in diameter. Can you imagine how much that is? The scale of these are so small, and the moment the confinement is broken, the plasma comes into contact with the outside world and it's cooled down. So there is absolutely no risk.
I remember the kind of news that came out, I think 10 years ago, and the discussion was, oh, they are going to create a mini sun on Earth, and that mini sun might actually turn out so big that it will just engulf the Earth. That's not true. That's so blown out of proportion. They are trying to create a mini sun. Yeah, they are trying to create a mini sun on Earth. But the point is, as soon as it breaks out of its magnetic field, magnetic tube that we call it, it is going to lose its heat. There is no reason to be scared of.
As soon as it comes into contact with the outside world, it's finished. And the scale of this mini sun that we're building is so small that we can't even sort of quantify it with our fingers. It's smaller than any of us can even visually imagine.
I also wanted to talk to you about the waste. So, what do you know about the kind of waste that would be produced? Because, as you know, when the term nuclear comes to being, the main cause of concern is the nuclear waste that is generated that does not decay for millions of years. And we have no way of getting rid of it. So it's just sitting in bunkers and it's just sitting in these cemented walls all over the US and all over the world, different locations. How are we going to, what is the waste and how are we going to handle it?
So the waste is essentially helium-4 or helium with two protons and two neutrons. And this is inert. So there is absolutely no waste that comes out of it. The only possible waste that we have to deal with is tritium, which inherently is radioactive and it has a half-life of 12 and a half years.
So, half life for our viewers means the radioactivity of a particle is going to be half of itself in that much time. For example, if the radioactivity of my particle is 50 units, then in 12 and a half years, it will be down to 25 units of radioactivity, and so on and so forth.
Okay, so essentially what Akhil's trying to say is that this has a half-life of 12 and a half years as compared to elements that come out of fission reactions, which have much longer half-lives comparatively. Also, if you look at it in a quantitative way as to the amount of waste generated by these reactions, the entire world, through all the nuclear fission that occurs in the world, generates 1.5 Olympic swimming pools worth of nuclear waste. Now, that is 3.75 million liters of nuclear waste. 3.75 million liters may seem like a lot, but if you think about it, your daily shower uses about 100 liters of water per bath. A dishwasher uses 40 liters per cycle, and a washing machine uses 80 liters per cycle. 3.75 million liters is not seeming so much now, right? It gets better because this is what's created by fission. Fusion creates 1,000th of this amount. So it's actually 3,750 liters of nuclear waste.
To add to this, thinking about 1.5 swimming pools for 10% of the world's total energy consumption is nothing numbers. And when you 10 times it, even those numbers are not at all bad to handle.
And that is with fission, not fusion.
And that is with fission, right? So we are not here sitting and saying that fission is a bad source of energy, because it is an absolute necessity and we should be investing heavily in nuclear fission reactors as well. However, when you take fusion into account and when you make those numbers 1,000th of this, then it seems unthinkable. It's like, what, 35,000 liters of water?
Give or take.
Give or take 35,000 liters of water for the entire world's consumption, and that water also degrades itself in 25 to 50 years. So and this is the dirtiest form of fusion. We have not even gone into the other kinds of fusion that can happen and the other kinds of fusion that are actually being looked into by the private sector.
This we're talking about the kind of the two kinds of fusion which we have told you about are the two kinds of fusion that are being done right now and that have been that are the most popular. There are cleaner and better versions out there which are still being researched. So that is a whole other video out there that we can do on those.
There will definitely be a podcast for the version 2 of this discussion, because this discussion is endless, right? And there are companies which are doing some amazing research in this. Some companies are on track for 2024 for a launch of their deuterium and helium-3 fusion, which produces no radioactive materials, if you can believe it.
Yeah. So what next? We're not saying that the problem is solved and from tomorrow onwards, all the world's energy is going to be fusion energy. This is a proof of concept experiment that has been done. There is a lot of drawbacks here because the energy that was used as input energy was a scaled down version. So this is not accounting for any of the energy that is lost by during conversion or all that kind of stuff. So there is obviously a lot in this that we are still missing. We have not solved the world's energy crisis. It's not like from tomorrow onwards, the world is going to have unlimited energy. This is just a proof of concept. The physics has been proven, and we can come to a point where we achieve a net positive energy outcome. Now, all this has to be worked on. The efficiency of the laser that was used is 0.5%. We have modern lasers in the world which can achieve a energy efficiency of 20%. That will greatly affect the final Q value that comes out of the experiment. So there is still a long way to go, but we can definitely see in the near future that fusion power becomes a reality and that we in the world start depending more heavily on fusion. And the fusion that was told to me as a kid was a pipe dream and that could never exist because how can we recreate conditions that occur on the sun on Earth is actually something that is a feasible outcome within our lifespan at least.
You know, there's this running joke between physicists that are working on plasma and physicists that are working on fusion itself. And the running joke is it's only 20 years away, and a year passes by and it's 20 years away, and then there is another year and it's 20 years away. It's always 20, never 19. And finally, it looks like it might be 19.
This is something that was never achieved before. This is something that holds the key to having energy that is not releasing carbon dioxide into the atmosphere, help us in combating global warming, in reducing the amount of carbon dioxide in the air, making the world a better place to live in, and just having an energy source that you don't need to think about that, oh my God, in X number of years, this is going to run out. There is no running out for fusion.
So I think the hope would be for more students to be pushed into the development of fusion reactors. More engineering students can be pushed towards this, and more physics students can be pushed towards understanding fusion a little better. Because even if we start building today, the reactors that have come into being and the experiments that are being conducted now were discussed 10, 15 years ago when they had to start building the reactor in the first place. So just like that, now is the time to push some money into this. And this is my opinion on this.
So we're talking about pushing money into this. So this discovery has happened in, I think, was it 6th or 7th of December? Yeah, I've just been reading. According to Bloomberg, this year there has already been $1 billion invested into fusion research. And this has followed the record-breaking 2.6 billion that was invested in 2021. So this is before anything has happened in the field. Today, this breakthrough, this discovery, this proof of concept that we have achieved is going to create so many more opportunities.
I think it's a glimmer of hope, and all we can hope is that somebody grabs onto it and the world flourishes forward.
Thanks for tuning in to another episode of the Thought Bistro podcast. I hope you enjoyed today's conversation and were able to learn something new. If you liked the episode, please be sure to subscribe to our show and leave a review on your favorite podcast app. You can also follow us on social media. Our Instagram and Twitter handles are available in the show notes. Thanks again for listening, and we shall see you in the next one.